Academic misinformation harms more than careers. It can distort clinical decisions, waste resources, and ultimately affect individual health. That is why initiatives like World Cancer Day exist to promote reliable, evidence-based information. Now look at what happens inside the literature. When we search retraction records for cancer-related research over the last 5 years, we see a large number of papers that were withdrawn from the record. As publication volume grows, the volume of misleading or unreliable work grows too. In practical terms, this is close to 1 cancer-related paper per day being retracted or flagged. And the reasons are serious. Across biomedical retractions, the dominant drivers are academic misconduct and major scientific errors. Roughly 60 to 70% relate to misconduct. About 20 to 30% relate to major errors. Either way, the result is the same: published findings that cannot be trusted. Now imagine the scale editors face. Submissions arrive faster than any traditional editorial team can deeply verify, especially before peer review even starts. That is why machine learning screening tools are emerging, not to replace peer review, but to help identify risk patterns early, when it's still easy to pause, check, and ask for clarification. Similar screening models are already being used in real submission workflows by some major publishers. They run before peer review as a first-pass integrity check, helping editors spot higher-risk manuscripts early. They don't replace editorial judgment. They help focus attention where extra verification is most needed. So how can we build such a model? At ML in Health Science, we built Retract, a screening app that checks whether an abstract resembles patterns seen in recently retracted research. The workflow is straightforward. Here are the key steps. Step 1, data collection. We start with retraction databases and collect records that match a target domain. We manually filter to true research articles and extract abstracts because databases can contain notices, duplicates, or incomplete entries. Step 2, build the dataset. Use 2 groups, retracted abstracts and matched non-retracted controls. Split into training and validation so the model learns signal, not noise. Step 3, training. Fine-tune a BERT-based text classifier on the labeled abstracts using a platform like Hugging Face. Monitor precision, recall, and AUC, and choose a conservative threshold to prioritize high precision. Step 4, deployment. After training, deploy the model as a private inference endpoint and connect it to your app. This trained model is deployed on our platform, and this video shows how retraction screening works in practice. Simply paste an abstract into mlhs.inc/retract to get a retraction risk score and a short AI explanation. MLHS currently provides 3 domain models: Cardiovascular, 600 retracted abstracts; Oncology, 1,200; and AI/ML and Digital Health, 700. Each model is field-specific and answers one question: does this abstract resemble patterns seen in recently retracted papers in this area? If you are an author, use it as a pre-submission check. If you are an editor, use it as an early screening layer. If you are a reviewer, use it to prioritize where to look first. Try it yourself. Open the MLHS Retract web app, paste the abstract only, and see what the model reports.